Hello, my name is Faraz Alam, and I am part of Embedded Systems Spring 2020 Team Three's capstone project. My other group members are Brad Ferguson, Sean Jocker, and Arash Vapor. To give you an overview of our project, basically the Infinity Stones have been scattered again, but this time they've all landed on the special playing field that you see here. In order to grab the Infinity Stones before Thanos gets his hands on them again, we're going to use a three-wheeled rover with a pixie cam attached to it. The pixie cam will be able to determine the color of each Infinity Stone, which will be very useful. And we'll also have IR sensors attached to the rover, which will be able to determine the distance between the Infinity Stones and the three-wheeled rover, as well as a claw attached to the rover where it'll be able to pick up the Infinity Stones and then take them over to the autonomous sorting area. A big reason why we want to use a rover is because there's an excess amount of gamma radiation um, emitting from the stones. So if any of us touch it, we'll just drop dead. Anyways, so at the autonomous sorting area, once the stones reach there, the robotic arm, which also has a pixie cam attached to it, will determine which crate the stones will go into based off of the color. Once it's stored in each crate, it'll be stored away from Thanos' hands and will all be saved. Now we've divided this project into four parts: rover, rover sensors, arm, and arm sensors. And unfortunately, due to the COVID-19 pandemic, we could not integrate all our components, but we will be showing you how each of our components work individually. So hopefully that'll give you an idea of how it all works together. And first up is Brad Ferguson with the rover demo.
So I'm going to send a command that goes just straight.
As you saw from the video, the rover can move in a straight line. The rover also has a capability of receiving other commands, like moving backwards, or rotating left or rotating right. To get into the specifics of how I did this, we first need to know how the rover actually works. So the motors that spin the wheels receive commands from the TI boards with speeds ranging from -127 to 127, and it can only be integers. So -127 is the maximum speed the motor can turn counterclockwise, 127 is the maximum speed the motor can turn clockwise, and 0 would mean that the motor is stopped. When the motors move, they actually have a counter that counts every time it spins a little bit. So when it counts positive when it's moving clockwise and negative when it's moving counterclockwise. And this count is read, and we can do it over an interval to get a relative speed of what the motors are. And with that speed, we can use a PID algorithm to make sure that the rover actually moves straight, because the motors will move at a speed that we actually want it to move and not just at a random speed, even though we said to set it at a certain one. So the PID algorithm is a common technique used to correct values for a closed feedback loop, which our rover is. And PID stands for proportional, integral, and derivative. So how the PID algorithm works is by summing all the errors from PI and D and adding them to the set point to get a new output to adjust. So if the previous value is lower than the set point, it'll tell it to run higher, and then if it's higher, it'll tell it to run lower. Now, if you see from the picture, SP is set point and previous value is the previous value that we just read. And we subtract those to get an error, and that error is used with our techniques of P and I. We don't use D for our rover. P just uses the previous error multiplied by a constant, and I uses a cumulative sum from the entire time that it was set at that current point, and then it will have a output that will add with the P and the set point to get the new output. Both of them have constants, and those constants can be used to see if our PID algorithm is working correctly. So here we have our graphs, and there's a lot of stuff to take in, but if we start from the left, we can see that it's speed versus time of motor 0 at set speed 64 with a Kp of 0.8 and a Ki of 1. Now Ki, the constant Ki is for the integral, and when that's high, it should oscillate like it does in the graph. Green is our desired speed, 64, and then blue here is our output from our PID algorithm, and A is the value that is the previous value that we were reading from the encoders. So as you see at the very beginning, it starts at 0, and when it gets set at 64, the encoder speed that we're reading on the motors is lower than the actual speed because it's just starting up. So it sets the speed on the motor to be higher than what it is, so it'll adjust and it goes high, and then when the encoder eventually starts reading higher values and it's spinning faster than what should be, it goes back down. And it does that for the entirety of 2 seconds. And the second graph here is when I fine-tune the PID constants. So here we have a low Ki and a pretty average Kp, and at the very beginning it's at a low speed, and then it adjusts high, and then it quickly levels out to the set speed of 64. And this is what really makes the motor that we make sure that we're running at the correct speed so that the rover actually moves straight.
Hello, this is Faraz Alam, and I will be doing the rover demonstration. Right now I have my wooden contraption here that holds my long-range sensor right here, and then my Pixie cam right here, and then my short-range sensor over there, right underneath the Pixie cam. I also have the TI board attached right here so that all the connections can be close. Normally this would be all these components would be placed on the rover itself, and it'll be all be powered by that power brick right there, but because of the pandemic we cannot demonstrate like that, so I'll have to demonstrate my component individually like this. So right now, as you can see from the terminal and the graph, the top graph is what shows my distance, and the bottom graph is what shows my PixieCam data. The PixieCam data does not have any data that it's receiving right now. That means it doesn't detect any blocks, even though there's a block right there. But that's because the sensors are facing upward against the ceiling, and right now it's telling me that the distance between the rover and whatever object it sees is about 175 or around 170 centimeters, which is about right. I measured that with a couple meter sticks. But let's see if it detects the red block as it should. So if I place it down like this, you'll see or place it up like this, you'll see that the distance has decreased significantly, and it's detecting signature 1, which is the red block. Okay, and then I'll just go over each block step by step. So this is the yellow block. This should be signature 3. Which it is. Okay. And then this is the orange block, which should be signature 2. Yep. Okay. And I moved a little closer, and it's telling me I'm approximately 15 centimeters away, which is just about right. And if I put the green block right here, the green block is about the 6 centimeter line. My contraption's at 24, so it should be about roughly 20 centimeters, and it should detect signature 4. There you go. So yeah, so it should detect signature 4. I'll hold it out like that. Okay, and then the final block, the blue block, I'll put it at this corner, and then I'll just hold it out like that, and it should give me about signature 5, and the distance is about, because I'm at a diagonal now, it should be about 30 centimeters, which it is, right? Oh, actually, just give me 22. Oh, okay, so this, sometimes I do get some garbage data, but it should be about 30 centimeters. Okay, and I will go over following this, I'll go over the reliability and robustness of this design and any flaws that I've discovered with it. But before that, I'll discuss how this whole system works. So this is the IR sensors and the PixieCam2 task diagram, or also known as the Rover sensors task diagram. This is very similar to the ARM sensors task diagram, so hopefully it'll explain a bit of that before it gets demonstrated later on in this video. So first thing I want to go over is the ADC reading task. This is one of the threads that are running. This task will basically grab the ADC readings from the IR sensors every 25 milliseconds because that's what the ADC timer is set at. So every 25 milliseconds, a message is sent to the get this interrupt queue. ADC reading task will grab that data, add it to a variable. It'll add it to this variable up to 20 times, and then take that average of that variable, and that'll give us a very accurate distance that it sees, and it'll send that data to the Pixie queue. Now the next thread I want to talk about is the PixieCam2 spy get blocks test. This is very similar to the previous thread I just talked about. The SW timer is set at 1 second for the Rover sensors. Every second it'll send a message to the get blocks interrupt queue. This will tell the get blocks task to call the spy transfer function, which indirectly calls the spy callback, and this callback will send data such as the most important piece, the signature, to the Pixie queue. And so the Pixie queue will receive two types of data, and will send all this data to the confirm object task, where it'll be determined which topic each data will be sent to. And once it's determined which topic it goes to, it'll send this to the MQTT message queue to the final thread, the MQTT task, which will send that data to the MQTT server. Now, as for the constraints for the Rover sensors, we meet all our test cases for the Rover sensors. We make sure that the short IR sensor is giving good data, as well as the long IR sensor, long-range IR sensor. We make sure that the both sensors work in conjunction with each other, and that the PixieCam2 can see color and also determine when a block or infinity stone has left its field of view or entered its field of view. As for reliability, this can definitely run for many hours. However, I did have some IR sensors fail, but this was due to some bad connections. As for robustness, as you saw from the end of the video, if the sensors are moving too much or just randomly, we'll get bad data, but this does not occur very often. A big issue that we do have is light in a room can severely impact the PixieCam2. So as long as you have constant light, it should work, but sometimes that's not something that you should rely on. So up next is Sean Jocker with the robotic arm and Arash Bipor with the arm sensors.
Alright, for the robotic arm, it uses 4 microservers that are connected to the TI board. Each servo is connected to 5 volts external power, ground, and a wire that connects to the TI board that receives the PWM command that updates each board's position. Using an algorithm we made, the TI board is able to increment each servo every 20 milliseconds or so, which steps the degrees of each servo until it reaches its final position. For the final arm component, we set up a GUI that sends MQTT messages to the arm, and it is able to convert these JSON payloads into degrees, which then it converts into PWM positions. The messages between the ARM server are JSON payloads, like said. We did this because it's just an engineering standard. The JSON payloads set specific servos in the payload. The robotic arm also has 3 threads: one that controls the movement, the one that connects to the Wi-Fi, and one that is able to do the algorithm. In the video we have here, I show an example of our GUI and 2 example left and right and reset that are able to step through a series of movements that we were going to use in our final implementation. You can also see that there is no connections to the laptop to the arm, so it is fully autonomous in this.
Hi, my name is Arash, and today I'm going to be talking about
my part in my embedded systems final project. I'm from Team 3, and I'm responsible for the arm sensors component. So now I have a demo video I wanted to show. So I'll allow the video to run a little bit, but basically this is how the arm sensors component looks like. That blue block is basically representing the blue infinity stone, and then on the left, you can't see it right now, but it represents the red infinity stone. And so here I'm just showing, oh, it's able to detect the, that's the vision, or that's the view of the camera. And so now I'm going to show, okay, the blue infinity stone has been brought by the rover, like simulating that. So it's being detected. And here I'm just going through and showing, okay, the blue infinity stone is signature 1, which is above, and the red infinity stone is sorry, that's the opposite. The blue infinity stone is signature 5, and the red infinity stone is signature 1. So right now, the server should be obtaining information from signature 5, which is the blue infinity stone. And so here I'm just talking a little bit, and let's see. It's just showing that blue light is just showing that it is a blue object that's being detected. So there, it's hard to see, but the blue infinity stone has been, detected, basically a space stone, which is the name for it right now. And it has all its corresponding information being sent to it, like its length, height, x and y location corresponding to the for the camera, like in pixels, basically. And so right now I'm just moving. Basically, right now I'm showing that it's not just outputting a constant information. That it like basically where the object is will grab that information corresponding to the camera. And so as you can see, the x and y are changing, corresponding, decreasing, because like the x has been the center, right, has been, the center of the block being detected has been moved to the left. And right now you can't see it, but if I rewind, I can talk about it when the red infinity stone has been detected. If I can move that, let's see. Yeah, so then here I'm just showing, okay, nothing is in the arm sensor's view, so nothing should be outputted. So then yeah, nothing is being outputted. I was scrolling down to show that I can't scroll anymore, but now I'm gonna move the red block, or the red infinity stone, to show that it's gonna be detected, and it's as signature 1. It's represented as signature 1. And so I walk over here and I show that, yes, see signature 1, and you see above signature 5, showing that the blue infinity stone was detected, but now it's the red infinity stone that's being detected, and its corresponding information. And basically, it's the red infinity stone is the reality stone in this case. And so, yeah, and I think that is the rest of my demo. Yeah. So that's basically, showing the whole operation, that the arm sensors component and the infinity stone has been retrieved from the rover, that it can grab it, extract the information, see, oh, okay, what type of stone it is, the information of where it is, and all that, and send it to the arm through the MQTT task, which is then shown on the MQTT server. Here I want to just talk about an analysis of it. Basically, weaknesses is the infinity stones are reliant on color. So if there are falsified rocks that look like infinity stones, they could be misinterpreted as infinity stones. Strengths are that the infinity stones will be detected if they come in view, no matter what. and robustness and reliability. The arm sensors component is reliable. It just needs to be put at a specific. It'll be always be put at a specific distance from the arm component so that it's always consistent with the information that it's gathering and being sent. For the goals of our arm sensors component, it meets them all, and the arm sensors component is able to detect the infinity stones when placed into view, and it's able to basically notify the arm when to pick it up and where to pick it up and what infinity stone is it that it picked up so that it can be placed in its corresponding gauntlet crate. And yeah, thank you so much.
So this concludes Team 3's senior capstone project for Embedded Systems Spring 2020. Thank you all for tuning in, and I hope you all enjoyed. Thank you.
I am inevitable.
Team 3.